Welcome to this comprehensive analysis. Please note right at the outset that this broadcast is an AI-generated audio review.
Right, yeah. We want to be totally transparent about that up front.
Exactly. So, to kick things off, I want you to imagine trying to build a massive, modern skyscraper.
Okay, I am picturing it.
Now, instead of providing a master blueprint, a solid concrete foundation, and standardized materials, the project manager basically asks every single construction worker to just forge their own steel.
Oh, wow.
Yeah, to mix their own concrete and design their own safety protocols completely from scratch.
That would be an absolute nightmare. I mean, the chaos would be unbelievable.
Right, you would face massive delays, catastrophic budget overruns, and, well, a structure that is just fundamentally unsafe to even step foot in.
And yet that level of severe fragmentation it's precisely the reality that a lot of fast-growing tech organizations experience today.
It really is.
Companies hire these incredibly talented software developers to write valuable business applications. But, those developers end up spending more than half of their working hours just configuring cloud infrastructure.
Yeah, setting up complex databases and debugging fragile deployment pipelines. It's a huge time sink.
Exactly. It creates this massive cognitive load. When engineers are totally exhausted by infrastructure management, they just have no mental energy left for actual product innovation.
So today we are doing a detailed technical review of the concepts presented in the Platform Engineer's Handbook by Ajay Chankramath.
It's a fantastic resource.
Our mission here is to explore how organizations can design, build, and scale a modern internal engineering platform to solve this exact problem.
Right. The overarching goal being to understand how treating an internal platform as a curated, high-quality product can radically improve the developer experience.
While simultaneously maintaining strict security and operational discipline, of course.
Crucial point. The central premise we really need to examine is that just, adding some automation scripts to a system that cannot fix organizational friction.
Right, scripts aren't enough.
Exactly. A true platform provides intuitive golden paths. These are standardized, highly automated, and heavily tested workflows.
And the key is that developers choose to use these paths not because management forces them to.
Oh, spot on. They use them because these workflows actively remove friction and make their daily jobs significantly easier.
So, to build this kind of system, the platform team has to adopt some pretty strict core principles from day one. The text really emphasizes the necessity of domain-content repositories,
Yes, that is foundational.
meaning the underlying code of the platform is physically separated by its specific area of responsibility. Like the code that manages computer networking is kept entirely separate from the code managing identity security.
Right, so you don't end up with one giant, unmanageable block of tangled instructions.
Exactly. And furthermore, the architecture relies heavily on trunk-based development.
Which is so important. I mean, in software engineering, when multiple people work on the same code, they often create separate branches to isolate their work.
Right.
But if those branches remain separate for too long, merging them back together causes massive conflicts. It leads to infrastructure drift.
Yeah, a complete headache.
So trunk-based development forces engineers to integrate their small code changes into a central main branch really frequently.
Right.
Like often multiple times a day.
Just constantly syncing up.
Exactly. It ensures that the entire team is always working with the most current, stable version of the platform.
The foundation also requires a robust tool stack. We see strong recommendations here for utilizing tools that offer free tiers, which really lowers the barrier to entry for new platform teams.
Oh, absolutely.
This includes using GitHub for source control management, CircleCI for automated testing pipelines, and Bitwarden for securely storing cryptographic secrets.
And Pulumi for defining infrastructure as actual code, plus Kind and Helm for local testing and packaging.
Right, it's a very solid stack.
Yeah.
So once those foundational rules and tools are firmly established, you need a highly reliable engine to actually run the applications.
And Kubernetes remains the undeniable industry standard for this runtime environment.
Yeah, there's just no getting around Kubernetes.
No, there really isn't. The primary reason for this dominance is its declarative APIs.
Which is a huge shift. I mean, in an older imperative system, an engineer writes a script that basically says, create a server, then install this software, then open this network port.
Right, and if the server crashes, the system just stays broken until a human actually intervenes.
Which is terrible for uptime.
Yeah.
But a declarative system operates on an entirely different philosophy. You simply describe the final desired state of your infrastructure in a configuration file.
You literally just tell Kubernetes, hey, I require 3 web servers running this specific version of my application.
And then Kubernetes just constantly monitors the environment in the background. If one of those servers suddenly loses power, Kubernetes detects the discrepancy between your declared state and reality
And it automatically creates a new server to replace the failed one.
without any human intervention whatsoever.
It's brilliant. But managing this powerful engine does require a strict separation of operating environments.
Right.
On one side, the organization must establish a platform sandbox and a platform preview environment.
Okay.
And then on the completely opposite side, they must maintain the app dev, app ca, and app prod environments. Those are strictly reserved for the application developers.
Now, I want to examine the necessity of that separation for a second. Why is it strictly required to physically separate the platform team's sandbox from the application developer's dev environment?
It's a fair question.
Because it seems like maintaining two completely distinct development clusters would just simply double the cloud hosting costs.
It might seem that way, but the separation is absolutely essential for systemic stability. It all comes down to the concept of blast radius.
Blast radius, okay.
Think about it. Platform developers are building the underlying infrastructure. They need a completely safe, isolated space to experiment, test new networking rules, and even intentionally break the cluster while they build new features.
Oh, I see.
If they shared a development environment with the application teams, a broken infrastructure update would instantly sever database connections or crash the runtime for every single app developer in the company.
Which brings all actual product work to a grinding halt.
Exactly. The sandbox provides that isolated space to innovate without causing widespread organizational disruption.
Makes total sense. But of course, a functioning runtime environment is entirely useless if it is not heavily secured and strictly monitored.
Oh, security is non-negotiable.
The architecture here mandates a zero-trust networking model. Historically, once a software service was safely inside the corporate firewall, it was trusted implicitly.
Right, the old castle and moat approach.
Exactly. But zero trust means no service automatically trusts another service, regardless of its location on the internal network. Every single request between applications must be authenticated and authorized.
And this is usually paired with OAuth integration for managing user identities and role-based access control, or RBAC.
Right, to ensure users only possess the exact digital permissions they need to perform their current task. Nothing more.
Following that security perimeter, the platform must also possess deep observability.
Yes, very different from just monitoring.
Exactly. Basic monitoring simply tells you if a system is broken. Observability provides the context to tell you exactly why it is broken.
And the architecture relies on the 3 pillars of observability, which are metrics, logs, and traces.
I love the medical analogy the book kind of inspires here to understand how these 3 interact.
Oh yeah, walk us through that.
So, metrics are essentially the heart rate and blood pressure of the system. Tools like Prometheus gather data to tell you that, say, CPU usage is dangerously high at 90%. Then logs provide the specific journal entries of the application. A tool like Loki stores the exact text error message stating that a database connection failed at line 42 in the code.
Right, so that gets you closer to the actual problem.
Exactly. And finally, traces act like a GPS tracker. A tool like Tempo follows a single user's request as it hops from the website front end to the auth service and finally to the database.
And then by utilizing a visualization tool like Grafana, the platform team pulls all 3 of these pillars into a single pane of glass.
That unified dashboard is absolutely critical during a system outage. When an application fails, engineers just do not have the time to log into 5 different servers to read disconnected text files.
No, they need it instantly. The single pane of glass ensures all that diagnostic data is correlated and right there.
Exactly.
I do have to challenge the sequencing of this development process, though.
Okay, let's hear it.
Does implementing such strict zero-trust security measures and highly detailed observability systems super early in the process stifle the initial launch velocity?
It's a common worry.
Because it feels like a massive amount of architectural overhead to manage before the team has even deployed a single useful business application.
Yeah, that concern is frequently debated among technology executives. It is commonly referred to as the security velocity trade-off.
Right.
However, baking security and observability into the architecture from the very beginning actually prevents catastrophic delays later in the software lifecycle.
Oh, so.
Well, if a team attempts to retrofit strict security protocols into a platform after, say, 50 application developers are already using it, They will inevitably sever established network connections.
Ah, they'll break existing developer workflows.
Exactly. Which severely damages developer trust. Early investment in security is really the only way to guarantee long-term deployment velocity.
That makes a lot of sense. And ultimately, the real test of this secure platform is the developer experience, or DevEx.
Yes, DevEx is everything.
The platform team really needs to deploy a demo microservices application very early in the building process.
Right, as a tangible test to evaluate if the platform actually reduces the cognitive load on the user.
Yeah, because if the process of deploying a simple demo app requires reading a 50-page manual or submitting 3 different IT support tickets, the platform design needs an immediate revision.
It's failed its primary mission. Having a secure, observable, and functional core platform is totally meaningless if developers cannot easily interact with it.
Which leads us perfectly into the concept of the developer portal, specifically utilizing open source frameworks like Backstage.
Backstage is huge right now.
It acts as the centralized digital storefront for the platform. It's a single web interface where developers go to read technical documentation, request new cloud databases, and monitor the health of their currently deployed services.
But we have to mention the stark warning the text provides regarding these portals. It really cautions against building what it terms a portal of peril.
A portal of peril. I love that phrase. I visualize this phenomenon by thinking of, like, a beautiful Hollywood movie set.
Oh, that's a good way to look at it.
From the front, it looks like a fully functioning city block. But when a developer opens a door to grab a database, there is literally nothing behind it but empty wooden scaffolding.
That metaphor captures the danger perfectly. A portal of peril occurs when a platform team deploys the sleek user interface of the portal before the underlying automation scripts actually exist.
Right. So if a developer clicks a button in the portal to provision a new testing environment, they just receive a loading spinner.
But nothing actually happens in the background because the integration is unfinished.
That developer will abandon the portal immediately.
Exactly. And regaining that lost trust is incredibly difficult. The functional automation must always precede the user interface.
Okay, so once the portal is backed by real automation, the platform has to offer seamless self-service onboarding.
Yes.
When a new engineering project begins, the platform automatically creates the necessary Kubernetes namespaces, assigns resource quotas, and configures the role-based access controls.
None of this should require manual ticketing or human approval processes.
And this automation extends deeply into CI/CD, or continuous integration and continuous deployment. CI/CD really must be treated as a composable platform service.
Right, where the platform team provides standard, heavily tested workflow steps like compiling the code, running security scans, and deploying the software container.
Supplied as pre-configured templates. This composability functions exactly like an automated factory assembly line.
Yeah, exactly.
You do not want every single engineering team in your organization inventing their own unique way to assemble a software product. You want standard automated blocks.
The application developers simply supply the raw materials, which is their code, and the assembly line handles the rigorous testing and deployment processes uniformly.
Moving beyond just compiling and deploying application code, developers obviously also require foundational infrastructure.
Right, they need relational databases, caching layers, message queues to actually make their applications functional.
And to solve this challenge without forcing developers to learn complex cloud provisioning languages, the platform utilizes a technology called Crossplane.
Crossplane is a fascinating mechanism. It is an extension that allows Kubernetes to manage external cloud resources.
Okay.
It enables the platform team to create infrastructure as code blueprints. These blueprints define exactly how, say, an Amazon or Google Cloud database should be built according to the company's strict security standards.
So the complex configuration details are entirely hidden from the developer.
Exactly. They simply request a standard database through the portal interface.
And this high level of automation culminates in the creation of starter kits.
I love starter kits.
They are highly opinionated software templates published directly in the developer portal. Because of these kits, a brand new engineering project starts with a functional code base, a fully wired up CI/CD pipeline, and strict security defaults fully operational on day one.
It's incredible. The developer simply selects the appropriate kit for their language, like Python or Java, and literally within minutes, they have a fully compliant environment ready for their business logic.
Now, as the platform becomes popular, self-service deployment is going to accelerate massively across the organization.
Oh, it will skyrocket.
So the company must ensure that all these rapidly deployed applications remain compliant with corporate security standards. And manual compliance reviews by human security engineers simply cannot scale to match this velocity.
They cannot. Therefore, the platform must implement policy as code.
Policy as code.
Yes. The architecture utilizes Open Policy Agent, specifically deploying a component called Gatekeeper as an admission controller.
Okay.
This system utilizes a specialized policy language called Rego. And this technology allows the platform to really shift policy testing left.
For you listening, in software engineering, the phrase shifting left means moving testing, validation, and security checks as early in the development cycle as possible. Moving left on the project timeline.
Exactly. By defining security policies as actual executable code, Gatekeepers physically intercepts every single deployment request.
Wow.
So if a developer attempts to deploy a software container that requests dangerous root-level network privileges, the admission controller checks the Rego policy, sees the violation, and automatically rejects the deployment.
So the non-compliant application is completely blocked from ever reaching the runtime environment in the first place.
Yes, it stops it dead in its tracks.
That's powerful. But this level of automated provisioning naturally introduces a new, complex challenge, right? Cloud resource waste and cost optimization.
Oh yeah, the bill always comes due.
Exactly. When developers can provision databases with a single click, infrastructure costs can spiral out of control really fast. This requires the practice of FinOps, which integrates financial accountability directly into cloud engineering.
The architecture addresses this by utilizing tools like KubeCost to make infrastructure spending highly visible to the engineers who are actually utilizing the resources.
Right.
It also mandates auto-scaling strategies to ensure cloud resources are only consumed when there is active user demand. But what is particularly fascinating here is the psychological difference between two financial management models, chargeback and showback.
Right. This is a great distinction. The chargeback model involves literally billing individual engineering teams for their specific cloud usage.
Taking money right out of their departmental budgets.
Exactly. Which often creates an adversarial relationship between engineering and finance, causing organizational friction. The showback model, conversely, simply shows teams their cost impact on a shared dashboard.
Displaying this data publicly leverages behavioral economics.
Yeah.
It provides visibility that naturally encourages teams to optimize their own usage without the hostility of an internal invoice. It creates a culture of pure accountability rather than top-down punishment.
It's a much healthier dynamic. Now, as the platform scales efficiently, it's also vital to prepare for inevitable system failures through resilience automation.
Because things will break.
They will. The operational standards require defining service level objectives, or SLOs, to measure reliability mathematically. It also requires establishing disaster recovery protocols using tools like Valero.
Valero is great. It automatically backups and restores the entire cluster state in the event of a catastrophic failure.
But a critical component of validating this resilience automation is a practice known as chaos engineering.
Yes, chaos engineering.
Now, I must push back strongly on the underlying logic of this.
Okay, let's hear it.
Deliberately breaking production infrastructure just feels entirely reckless. If I am a chief technology officer, how do I possibly justify taking down the primary checkout service at 2 in the afternoon on a Tuesday just to prove we possess the ability to fix it?
It sounds crazy, right?
It sounds akin to intentionally playing with fire inside a wooden structure.
That is a highly logical concern, and honestly, it is a reaction that many executives share when first introduced to the concept.
I would imagine so.
However, the engineering reality is that complex distributed systems are fundamentally fragile. They will inevitably break regardless of your best intentions and rigorous testing.
Okay, sure.
Chaos engineering does not create the systemic weakness. It simply reveals the existing weakness on your preferred schedule.
So it is the difference between a controlled detonation and an unexpected explosion.
Exactly that concept. By deliberately breaking components during controlled daytime hours when all the engineers are fully caffeinated, watching the dashboards, and actively communicating, you safely validate your automated recovery tools.
Right, because everyone is ready for it.
Exactly. If you wait for a natural failure to occur, it will inevitably happen at 2 in the morning on a Sunday.
Which is the worst time.
Right. During off hours, response times are significantly slower, human error increases due to fatigue, and the negative impact on the business is maximized.
Okay, that reframes the operational risk completely for me. Finally, to remain effective and scale indefinitely, platforms really must evolve beyond static, rigid automation rules.
They have to.
They must prepare for AI-augmented platform operations. Generative artificial intelligence is positioned as a profoundly transformative tool for developer workflows.
Oh, without a doubt. The architecture details specific, highly practical use cases for this technology. One major example is AI-powered CI/CD pipeline generation. In this future scenario, developers will not need to write complex deployment scripts manually. They will simply describe their deployment needs in plain English, and the artificial intelligence will construct the complex configuration files automatically, strictly adhering to all company policies.
That's incredible. Another use case involves incident triage bots. During a major system outage, human engineers are often totally overwhelmed by thousands of lines of system
It's
logs.
like finding a needle in a haystack.
Exactly. But AI agents can instantly analyze these massive volumes of data, cross-reference them with historical outages, and suggest the most probable root causes to the human responders within seconds.
Furthermore, the platform can utilize retrieval augmented generation, commonly referred to as RAG, to completely revolutionize technical documentation.
Oh, this is a game changer.
Instead of manually searching through static, often outdated company wikis, developers can just query an AI assistant. Because of the RAG implementation, this assistant actually understands the specific proprietary context of the internal company architecture.
So it can provide instantly accurate, localized answers.
Yes.
By implementing these technologies thoughtfully, the platform transitions from being just a passive set of automated tools into an active, intelligent partner in the software delivery lifecycle.
It's a huge leap forward.
It really is. We have journeyed from the foundational design principles of a domain-bounded repository through the implementation of automated infrastructure and right into the future of AI-augmented incident response. Which brings us to a final provocative thought for you to consider.
Yeah, think about this. If artificial intelligence can now accurately write infrastructure security policies, manage complex incident triage, and dynamically generate deployment pipelines based on plain text requests,
Right.
how long will it be before internal platforms become entirely self-managing autonomous agents?
Could this rapid evolution eventually remove the need for human platform engineers altogether? I mean, will the platform of the future simply build and maintain itself based on the changing needs of the business applications it supports?
That is a profound and maybe a slightly unsettling question for the technology industry to ponder as these automation tools mature.
Definitely.
For those who wish to deeply understand the exact code implementations, the architectural diagrams, and the practical configurations referenced in this analysis, I strongly recommend that you read the actual book, The Platform Engineer's Handbook by Ajay Chankramath.
Yes, definitely check it out.
The true value lies in seeing the execution of these complex concepts firsthand.
Absolutely. To all the friends of the show listening today, we ask that you subscribe to our feed so you never miss a comprehensive analysis. We wish you a great day, and we encourage you to keep questioning how your technology is built.